Welcome to a lesson with Dr. Powell. Let's take a look at what happens with a Hessian matrix, second derivative matrix, as we're trying to find scalars that this behaves like, that are both positive or both negative, and come up with a nice kind of technique or formula which is used in many books and other resources online. At least to describe the case when you have two input values, an x and a y. Okay, but this only works for that case. Okay, so if we take a look at the second derivative matrix, it looks a lot like this, except the second derivative actually, it should look like this, right? Where you have an fyx, it's fxy, and take the derivative. But a nice feature about the functions that we work with is actually fyx is actually equal to fxy. They're the same. Part of that comes from the idea that not only do we have a tangent plane approximation to a surface, but we actually have a polynomial type approximation. If you take any polynomial at all, like this, say, and you take a derivative with respect to x and then y, you'll notice it'll be the exact same as if you did the other way, y and then x. So let's just try that. With respect to x, we'd get y squared plus 2y cubed x, because that's just a constant. Okay, now with respect to y, we get 2y plus, and then we'd have 6y squared x. Right, with respect to y. Okay, now let's do it the other way. Let's first start off by respect to y. With respect to y, I'm getting 2yx plus 3y squared x squared. And then with respect to x, you notice you get this. You get 2y, and then bring that 2 down and just x. So you end up getting the same thing. And if you work out enough cases, you'll realize that yes, for polynomials it works. And it works in general because for our nice functions that we're concerned with can be approximated by these guys, and up close kind of the equality is kind of match, limit. So we're good. All right. So we're going to use that idea. Okay. Now what do we do? Now remember how we took the determinant of like x times a so with x's in diagonal minus everything else. Well, instead of using x here, because we're already using x right here, let's use a Greek letter lambda. This is something that pops up often in multivariable calculus, is this letter lambda, lowercase l in the Greek alphabet. So if we were to take the determinant now, so cross this minus that, we end up getting this right here. And if you multiply it out and combine the middle term, so this one times lambda, that times lambda, and factor out a lambda and the negative, you get this, and you get fxx, fyy becomes a plus, and then minus that. So now looking at this, we think this is the coefficient of lambda. This is like the constant term, and that's lambda squared. Now, if you ever thought about factoring something, a quadratic, so if we have something like x squared and we have a minus in the middle guy, all right, so thinking of an example, what if we had, let's do, what if we did 5, and we have a plus here, and we have, so thinking of that, so you have a 1 and a 5, and let's suppose you have x minus and x minus, right? You'd end up getting minus 6x here. So notice that whenever you're going to have the same sign appear here as here, something has to happen. You have to have a plus over here. That's essential. You have to have a plus over here to have the same sign, and that sign will be a negative if there's a negative here. In contrast, if we had something like x plus 1 and x minus 5, then let's see, then that would be x. So we get x squared minus 4x minus 5. Notice how we have a negative over here, and that results from that negative times that positive. So you have a difference here. So if we want to maintain the same sign, we better have this guy over here being positive. That'll be essential. We want that guy right there to be positive so that both of the roots will have the exact same sign. Now, if this root here happens to be a negative, then that means, or not the root, but this coefficient is negative. That means that the roots are going to be positive, right? So positive 1, positive 5 are the roots. So a negative here means the roots are positive. A positive here, so let's try that out. If that's plus, you could get the same thing by doing this, which would make these roots negative. So we think the same idea over here. We'd want this part right here, okay? So if this part right here is negative, then the roots will be positive. Well, in order for this to be negative, we need this guy and this guy. It'd be nice if both of them were positive, then this would be negative, but let's kind of think about that here. If we require that this be greater than 0, then we're actually forcing this part right here to be positive, because this is already negative with a square here. So this has to be positive, but in order for this to be positive, fxx and fyy have to have the exact same sign. So that means either they're both positive or both negative. So if they're both positive, then that means negative here, which means positive roots. So essentially we can just even check just one of them. If fxx is greater than 0, that means positive roots. That means a minimum. It almost looks like concave up even, right? Positive and so minimum. It makes sense. And then likewise, if fxx is less than 0, concave down, that would be like a maximum. So you could get that idea right there. And that's kind of where those conditions come in. So what are the condition statements? Let's see, I'm trying to think here. Yeah, before we go to there, let's just kind of review. This part right here has to be greater than 0 for both of the roots to have the same sign. If it's less than 0, they both have different signs. We call it like a saddle point because the derivative is like behaving differently in two different directions. One way it's like a minimum, the other way it's like a maximum. So it creates like a saddle. So kind of this way it's minimum, but that way it's not. So that kind of happens there in that case. So you can actually that's a nice check for saddle point if that's less than 0. If it's equal to 0, this test is inconclusive because one of your roots will actually be 0, and so you don't really know what's going on with that. But both of them really should be the same sign. So let's kind of write down what that condition is then in particular. So in general, if we need that fxx and fyy minus fxy quantity squared. This has to be, so if this is greater than 0, then we're in line for determining if there's a max or min. If fxx, which actually is the same as fyy, you could either check fyy if you wanted to, that's fine. But here they normally just say fxx, that's fine. X becomes before y in the alphabet, I suppose. So fxx greater than 0, that would be a maximum, or a minimum. Sorry, minimum. Okay, minimum. And fxx less than 0, like concave down, that would be like a maximum. All right. Then what if this quantity right here were okay? If this quantity were less than 0, that means we for sure have a saddle point. Just discuss that because the different roots will be different signs. Saddle point. And if it's equal to 0, then one of the roots is 0. So we don't know that they both have the same sign or different signs or anything. What's the sign of 0 there? It's just inconclusive is what we say. We can't really use this test very well. Maybe we'd have to do something else. But inconclusive in this particular case, if this right here is equal to 0. Now, one little note, we're talking a lot about the roots or the scalars that the matrix is behaving like. Those roots actually have a name. They're called eigenvalues for the matrix. So if you look this up somewhere else online or something like that, eigenvalues, so if a Hessian matrix has positive eigenvalues, then it's like concave up, so you have minimum. If a Hessian matrix has negative eigenvalues, then it's like a maximum, concave down. Thanks for watching.